Welcome to the last day of Global Hack Week and the second part of Data Structures and Algorithms in Python 102. For those of you who are new here, just tuning into this series, yesterday we went through the beginning of our series for intermediate data structures in Python. Last month we did a more beginner version of this stream series, but we're going to have it aimed so it's most people can dive in, and also as always, we'll have resources for y'all to catch up after the fact if you need to. All right, so before we dive into actually coding, I want to introduce myself before we get started. If you're new here, if you're new to Global Hack Week, if you're new to Major League Hacking in general, or you just dove into the first one of my streams, my name is Gabriella. I'm a coach here at Major League Hacking. You might see Major League Hacking referred to as MLH in other places, like in my background. There you can see it. MLH stands for Major League Hacking. So if you see that around elsewhere, just so you know, that's what it stands for. Outside of being a coach at Major League Hacking and running these stream series for Global Hack Week, I'm also a full-time software engineer. And I talked about this yesterday, but I just returned from a trip to Mexico City recently, and I had a lot of fun there. Highly recommend if you haven't been. I had a fabulous time in Mexico City. Also, I do want to highlight the registration link. Make sure that you register your attendance for the stream so that you're eligible for any swag drops that Major League Hacking may do throughout Global Hack Week. And also, this makes you eligible for different achievements throughout the Global Hack Week. And also it helps us to see which stream series our hackers are interested in and what is, I guess, like something similar we should do in the future. That helps us out as well. I do want to call out, I frequently have lots of short links in my slides. As you can see at the bottom, there are 2 short links, one for DSA 102 slides and one for DSA 102 code. Those are aptly named for the slides of today's presentation. And then the code that we'll be working on later, kind of like the structure of how this will go is I'll do a little bit of an explanation for some coding concepts. We'll talk through the tree data structure, do a little bit of review on binary search as an algorithm, which we talked about yesterday, as well as a little bit of a review on linked list, just to kind of solidify that understanding. And then we'll dive into some practice problems. I'll talk through my thought process and what we're looking for, so you can follow along. But we'll also have that code after the fact. If you get a little bit lost, there's a little of a lag on your Wi-Fi, or you just don't fully understand something in the moment. Awesome. And then, I do need to, my apologies for this. You can see this in real time, me editing this, but that is the registration link for yesterday. Here is the registration link for today. Oops. I'll put that up on the screen and type it in chat as well, so you have where you can register your attendance. But this is where you can register your attendance with Major League Hacking. I just shouted that out, and I'll put it up on the screen while I'm talking through what data structures and algorithms is, so you have a little bit of an understanding if you're new. I'm going to go through this a little bit quicker than I did yesterday, just because it's the second part of the stream, but it's here, just so you know. So for those of you who are just joining in, DSA stands for Data Structures and Algorithms. Data structure, as a definition, what it is, it's a way to organize, store, and manipulate data in the memory of a program. So within your coding languages, you'll have a few set defined data structures. These are things like list, strings, arrays, dictionaries, linked lists, trees, hash maps, hash sets. Those are some I'm thinking off the top of my head. There's definitely a few more, and sometimes the same data structure will have multiple names across different coding languages. Like an array is also a list. I refer to them interchangeably because I work both in JavaScript and Python. So sometimes the syntax gets a little bit blended, but the concept is largely the same. Also, an algorithm, for those of you who don't know, is a step-by-step programmatic rule for solving a problem. We went over the binary search algorithm yesterday. That's the only algorithm we're going to be going over today as well. We'll just be diving into trees in addition to a little bit of review and doing some more problems with the binary search algorithm we covered yesterday. But algorithms are useful because it gives you kind of like a set instruction or a formula for solving similar types of problems. And also it's helpful because you know kind of off the bat what the time and space complexity is of something. So when you're working on a project at your job or for a project for university, you're able to solve it a little bit quicker versus having to think through something and build it from scratch. You already know that binary search, for example, will lessen the time for your searching in whatever program by half. So that's a good thing to know, at least half, I guess, depending on how large your list or array is, but we'll get into that in just a second. I also wanted to shout out for those of you who aren't currently interviewing for jobs. Maybe you're just fresh into university, or maybe you're in software engineering and kind of content with your job. You're not looking to job hop. I think that these skills for data structures and algorithms are useful when you're actually an engineer and just kind of chilling, not actively looking for a job. I found them myself to make it a little bit easier to find connections when you're working through problems and when you're, I guess, studying these data structures, these algorithms. You're able to make connections and remember different details that make things a little bit easier or more efficient in your day-to-day job. And also me personally, I find that it's a little bit easier as well to think about the time and space complexity in my day-to-day work as well. If I am like thinking about those things not during work and going through these problems, thinking about and analyzing that time and space complexity. So that's kind of like in a nutshell what data structures and algorithms is. These make up whole university courses. So we'll just be covering kind of the tip of the iceberg today. But there's so much to learn with this, and it's a very useful skill set to have. Even if you don't want to get into software engineering, but just like tech broadly, these are useful skills to have because they improve your problem solving skills and also your technical communication skills with the way we're practicing DSA today. All right. Also, I wanted to shout out as well, if you have any questions, comments, feel free to drop them in the chat. I want to make sure that everyone understands what's going on. And if you notice that I made a stupid syntax error, please tell me, because then it will save us all some time when we're going through and solving problems. That's happened on more than one occasion, and I thank y'all for it. All right, let's see. We have someone who registered themselves. Love to see that. Make sure you register yourself. The link is in the chat and on the screen for a little bit longer. Oh no, I accidentally clicked on the link. But that's what you would do to register. Here we go. Up onto the agenda, a little bit of an overview. What else do we have here? Yesterday, you were looking for some data structure, Python material, and found my stream. Keep up the good job. I'm glad that you enjoyed it and you learned something. That's what we're trying to do here at Global Hack Week, and I'm excited that this is going to help you in your studying process. Awesome. Okay, so now on to the agenda. Yesterday, we did binary search and linked list. We'll do a little bit of a review of that today. And then after that, we're going to talk about trees. We're going to cover the tree data structure and do some practice problems. And then not on this agenda, we're also going to cover time and space complexity. Excuse me. Just because those are useful things to know And I want us to be able to talk about those a little bit as we're solving the problems later on today. All right, just got some water. So I'm going to do a quick overview of binary search right now, just so we can get a little bit of a refresher. Essentially, it is cutting the time complexity of searching in half. It'll use 2 pointers and a middle value. So this will be in a list or an array. Binary search assumes that your values are in ascending order. Similar to a 2-pointer problem, there's a start and an end pointer. So pointer 1 will be at index 0, and pointer 2 will be at the last index of your list. But you're also going to have a middle value, and that's found by taking the average of the two. And then essentially what you do is you compare your middle value to whatever value you're looking for. And then you will adjust your pointers accordingly to figure out if the larger pointer needs to be decreased to be 1 less than the middle, or if the smaller pointer needs to be increased to be 1 more in the middle. All right, so binary search in a nutshell. We did I think we just did basic binary search yesterday, and we have a problem or two we're going to cover today. And we did lots of linked list problems yesterday. I think we did 4 in total. Linked lists, for those of you who don't know or need a little refresher from yesterday, are a linear data structure that allow for a little bit more efficient insertion and deletion compared to a typical list or array. So a linked list has 2 basic, what makes up a linked list has 2 basic components. A, B, C, and D right here are all called nodes. And inside of a node, you have the value or the data, and then you have the next pointer that will point onto the next node. And then the last node will have a next value of null or none, because that's the end of the linked list. But it will have a null or none value versus just kind of like the last value being the value itself. This node right here, the first node is called the head, and the next value is referred to as the pointer. So yeah, that is what a linked list is. Now we're on to trees. Trees are somewhat similar to linked lists in that they are connected to one another, but they're not linear. So where a linked list is linear, trees are nonlinear. They are hierarchical in trees. And in trees, this data structure is made up of multiple nodes. So made up of the same individual items that a linked list is made up of. So each node will have a value, and then instead of having a pointer, it'll have what we call an edge. They function similarly. The only difference is they're nonlinear. So there can be multiple pointers or edges that are connecting a node to other nodes, creating this tree-like structure. I just want to point out all of the lines on this diagram that I have that are dotted are not edges or pointers. These are just declaring different values or subrelations of the nodes. So I wanted to call that out. But also something that's unique about trees is there's only one unique path from one node to the other because of how they're interconnected. It's going to be one unique path. And frequently, a lot of tree problems will have you connecting or will have you looking for the unique path of something or the shortest path of something. So if you're just looking for the end node that has like the shortest path to the root or the parent, say for example, like in this entire tree, it would be a 3-way tie for F, G, and H, because these are all of these are the end nodes in this tree, and all have a unique path of going from their individual node to C and then to A. While it may look like it's the same path because they're all passing through C, we do need to factor in that their unique path starts with themselves as a node. So that would be a potential problem. you'd be looking for. Usually they're a little bit more complex in what they're asking for. Sometimes they'll ask for what is the shortest path of a leftmost node? What is the shortest path of a node that has no children? Or what is, like they'll add a few like more qualifying things onto it. And it sometimes will have relevance to like a real world problem. Other times, a lot of times it's leak code and data structures and algorithms problems. You can't always immediately see the real world application, but frequently they will have a real world application that they just don't go into explaining because they want to just have the quick problem solved versus a large project application. Yeah, so that is kind of trees in a nutshell. Now I want to kind of talk through a few different aspects of trees as like far as like how they relate to one another. So similarly to linked lists, the beginning node has a name. It's called a root in trees versus the head in linked list. Sometimes these are also referred to as the parent node, but parent nodes aren't always the first most node in a tree. Sometimes they can also refer to where the node where there are two children or multiple children or just one child. If there's one coming off of it, it's like a parent node, but it can refer to a sub tree within the tree. So that's an interesting thing too. This like kind of applies in linked list as well. But if you segment it off, this is also a tree. If you're just looking at Dij, but it's just a subtree of the larger tree that's in this image. And this would be a parent node, and I and J would be children. Different nodes that come from the same parent node, so like different child nodes that come from the same parent node are called siblings. As you can see here, I and J are siblings, D and E are siblings from B, F, G, and H are siblings from C, and K right here is an only child, so it doesn't have any siblings. But different nodes that are from, I guess, different nodes that like off to the left or are in like the same area are called leaf nodes. So these will be right here. We have K and F. And also like these specifically as leaf nodes are nodes that do not have children. So these would be K and F within this diagram. And then these as well are technically leaf nodes, I and J, because they don't have children, as well as the end. All right. Also, something else I wanted to point out is that in a tree, they do have levels instead of indices. You can't access them like you can in a list or an array where you go tree or list name and then at like in brackets 0, 1, 2, etc. But they do have levels similar to indices that kind of help you mentally keep track of them. So these are 0 indexed, or I guess 0 leveled would be more accurate. So A is on level 0, and then B and C would be on level 1, and then these are all on level 2, et cetera, et cetera. So yeah, those are trees in a nutshell. These are helpful for grouping lots of data that doesn't always look super interconnected, because it's kind of like a computational mind map, if you will. So there is a path to get them all together, but they aren't always super related, just maybe under one broad topic of storing data. So yes, sometimes this can be how you group information about a person or user. This isn't, I would say, the most efficient way to do that, but that is like an example of how you could use this. Yeah. All right, so those are trees. Now I want to talk a little bit about time complexity. So like I talked about earlier, time and space complexity are things that you need to think about when you're working on problems. Frequently, when you're working on data structures and algorithms problems, you will have, you'll be asked for the time and space complexity in interview, and also the brute force solution, which is often the first or the easiest solution to think of from the get-go, will have not the best time and space complexity. So interviewers or your processor, to be honest, might fail because of like exceeding the time complexity of an application or tester. You'll want to move from a brute force solution down to a more optimal solution. So the most optimal solution, when someone says they're looking for the most optimal solution, essentially refers to a program that balances the time and space complexity. So they're both like relatively good. I put some basic time and space complexities on the slides. I'll talk through those in a second. But essentially, when I'm referring to time complexity, that's just measuring how many times a statement in an algorithm or a solution is executed. I know that it can be a little bit confusing when you're talking about time complexity or run execution time of the code. So like how you can differentiate the two and what to keep in your mind to keep them separate is that the time complexity is just how many times a specific statement is executed within the code versus the run execution time, which is how long it takes to run all of the statements. You might be wondering, if you're looking for the time complexity of a solution, wouldn't you want to measure and like add up all of those statements together to get the time complexity, because you want the time complexity of the entire solution and not just like one particular statement? But something with time complexity is if you have multiple, for like multiple statements, the value is the same, you simplify it. So if you have two statements in your program, say, for example, you have one line that says, hello world, it's just printing it. And then you have another one that's printing, my name is Gabriella, or like whatever your name is. And there's two lines of code. So the overall execution time of that would be 2 because there's the 2 lines and it's constant. But if we're looking at the time complexity, we simplify it because they're both constant statements. So it would just be O of 1 for that time complexity versus the execution time. So when you're looking at the time complexity, you're looking at the most complex statement it takes to execute in your program, and then you're simplifying. So say, for example, you had a for loop, which has a time complexity of O of n, and then you also have a print statement or a return statement outside of that for loop. You would technically have a time complexity of O of n, and then the next statement would have a time complexity of O of 1. But because the largest time complexity of any statement in your program is O of n, you simplify. So it would just be O of n versus O of n plus O of 1, because you don't need to have like all of that, because you're just measuring to see how many times it needs to execute and how it will scale in line with the data, not the execution time of the entirety of the program. I hope that explanation made sense. I'm going to kind of emphasize the differences, and so you have a little bit of a better understanding and overview of that. I do have linked on the slides a more in-depth explanation of both time and space complexity on the Geeks for Geeks site. I personally like Geeks for Geeks because they have all of those wonderful diagrams. I inserted a few into my slides earlier, and they explain it in a way that personally makes sense to me. I'm a visual learner, so the diagrams are very helpful, as well as breaking down different time and space complexities of different code samples. But yeah, that's time complexity in a nutshell. I do want to go over a few of these examples. I talked through what the time complexity of O of 1 would be. That would just be a basic print statement. Something's executing one time. This can be with interpolation. So something like where it says hello, and then in brackets it says name, and you have name declared earlier in the code as a variable. You'll get up to linear time complexity, which essentially means it's just scaling with how large a particular value gets. So this will be a basic for loop. So if you have multiple names, say, for example, I put my name and then all of the attendees of this stream into a list, and we looped through that and said, hello, Gabriella, hello, Dumpster Sally, hello, Dectoro. Those are the comments that I'm seeing. that would be a linear time complexity. And then for a time complexity of O of n squared, this would be if you have multiple for loops, also referred to as a nested for loop. I made a mistake when I was typing this up on the slides. I should have proofread these a little bit more closely, but I'll explain it when I'm reading it off, and I'll edit these slides after the stream. So what you have after the fact is accurate. But for example, if you had a statement that was for I in names, and then something like for I in reservations, and you went through to see if I was in the reservation. Not the most optimal way to do that, but that would be a time complexity of O of n squared. So if it was just for I in names, and then within the for loop for I in names for J in reservations, and then you printed something for within the for loop for J in reservations, that would have a time complexity of O of n squared. And again, I'll update that. I know that's a little bit confusing on screen. My apologies for that. Okay, now on to space complexity. So as far as space complexity, it is similar, but it's just referring to the memory instead of how long it takes to execute something. So you're just measuring how large the memory will need to get in order to solve the given problem. And don't confuse this with auxiliary space, the extra space that's used by an algorithm, which it kind of excludes the input of the problem. I personally don't find it super, as confusing to differentiate space complexity with auxiliary space. But if you have worked with more memory in the past, that might be something that is a little bit confusing to you. So just make sure that you keep those two separate. And remember that the space complexity is how much is required by the algorithm itself versus the extra space used by an algorithm. All right, so a few basic items for space complexity. If you're doing basic operations, so subtracting, dividing numbers, you're assigning variables like name equal to Gabriella, streaming service equal to Twitch, streaming service equal to YouTube, stuff like that. That's pretty basic. And then for a linear space complexity, which is also O of n, this will be storing items in a list or array because those need to get larger as you input more information into a list or array or a dictionary, whatever type of data structure you're storing your items in. And for space complexity, sorry, there's another typo at the last one. Not having great luck with my third items. But for the space complexity that is O of n, these will be for 2D arrays or matrices if you're using those to store information, because those will need to scale not only for each item in the array, but for all the items within those 2D arrays as well. And like I said earlier, I have a more in-depth explanation linked on the slides, so be sure to check that out if space and time complexity are something that's a little bit more fuzzy for you. All right, so now that we did a little bit of review on linked list and binary search as concepts, I introduced trees as a concept, and I talked about time and space complexity. Let's dive into a few more problems, or not a few more, but let's get started with practice problems. All of these links are from LeetCode, which is a pretty popular data structures and algorithms practice site. Those will all be linked for you to access later, and I'll share as I'm going through these problems in the chat if you want to follow along directly. Before we get started, I'm going to pull up searching a 2D matrix while I'm talking, but I'm curious how many of y'all have worked with Python before is my first question. And my second question is if you have worked with LeetCode or done any sort of like LeetCode style questions before. So if you could in the chat maybe put a 1 if it's yes for both, a 2 if it's yes to Python, no to LeetCode, and maybe a 3 if it's no to both. I'll give you all a second, and I'm also going to put the link to this problem in the chat as well, so you're able to access it if you want to follow along directly with me. All right. So it looks like Dumpsters Alley is familiar with Python and LeetCode. Again, it's okay if you're new. That's what the purpose of these streams are, is to learn. I just want to make sure that if y'all are already familiar with LeetCode, that I don't need to explain, I guess, like all the bits and bobs for how it functions. Oh, and you also solve daily challenges on GFG as well. Is that another DSA site? I'm unfamiliar. Or like an algorithmic programming site? All right, and we have someone else who is familiar with LeetCode, but in Java. Maybe they're new to Python. I do think that Python is the best language to interview in if you're getting ready to look for jobs or looking for jobs right now, just because it's, I think, the easiest to pseudocode and then kind of translate from basic English into coding. But if you're like super proficient in another language, then obviously that's not the case. But if you're super new to this, I'd highly recommend Python. Okay. GFG is Geeks for Geeks shortened. I did not, didn't think that. Okay, nice. I didn't know they had daily challenges. I mostly use them as reference, but cool. Awesome. Okay, so now that I have a little bit of background on where everyone is for their particular experience, I'm going to get started talking through this problem, and then we can actually start solving it. We're going to be solving our problems today in Python. That's what I'm the most familiar with. It's been, I think, since my freshman year of university, since I've used Java in any serious sense. So I won't be using Java today, but the concepts themselves should be pretty transferable. And if you want to solve it in Java, as I talk through a potential solution, feel free. And that goes for any language, of course, as well. I'm just using Python because it's what I'm most familiar with. All right, so let's read off this problem. If you didn't tune in yesterday or to any of my previous DSA streams, what I do when I read through these problems is I write down a few things of, so what we're given, what we need to do, and then if we need to return anything. This is just me talking through a basic understanding of the problem so that I make sure that I'm confirming everything to like my proper understanding. And also I do this when I'm in a technical interview, although it's been a while since I've done a technical interview, as I'm, I don't know, I'm full-time engineer, so haven't been interviewing all that often. But anyways, regardless, this is a good thing to do when you're interviewing. It is a good thing to show the interviewers just your thought process. So even if you don't get the problem right, you're able to kind of show them your thought process. And if you were close, and also, are you someone that is able to clearly communicate your thought process and your different attempts? And are you verbalizing the different things you've thought of or tried to do? Because those are things they're also looking for in a software engineer. They're not just looking for someone who can memorize LeetCode problems or is like very good at data structures and algorithms, problem solving and like recognition. Those things are good things to have, of course, but they're also looking for someone that they can communicate with and who is going to be able to think on their feet as well. All right, so little explanation aside, let's get into searching a 2D matrix. This is a binary search problem, at least in the way that we are going to solve it, just as like a aside. But now we can talk through the problem and see what we're given and what we need to do. So we're given an m by n integer matrix. It's called matrix with the following two properties. each row is sorting in increasing order. I don't know why they decided to say sorted in non-decreasing order. Just, I don't know, say that a little bit more straightforward. I do have beef with some of the descriptions of these problems. They are not always the clearest. And this is why we need more software engineers who know how to properly communicate. But anyways, the first integer of each row is greater than the integer of the previous row. So both like the arrays that are in the array rows are in ascending order, as well as the first integer column is ascending. Both of those are ascending. But like I said, that would mean as well that all columns are ascending as well. I'm not 100% sure, but it looks like, at least in the examples they've given us, that holds to be true. I guess that has to be true, because if each row is ascending and then the first item of each, the first index, or the first index in each like part of the 2D list is ascending as well, then they would have to increase past that. Okay. So that is the properties of that. I've talked through that. And then we're also given an integer of target that we're looking for. So yeah, okay. And then if the target is not in matrix, then we return false. This is similar to the basic binary search problem we did yesterday. And yeah, so this is just kind of complicating it because it's in a 2D matrix. Okay. I don't know sorted in row and column wise what you mean by this. If you could extrapolate a little bit in the chat, but I'm going to continue on. I think you just mean like it's sorted like in increasing order, in which case that'd be correct. Okay, and also it's asking us to write a solution in O log m times n time complexity. This just essentially means we have to use binary search for our algorithm, because like yesterday, our solution was O of log n time complexity, because it was just a 1D list for our binary search problem. Okay, so what we're given a 2D list that is ascending both left to right and by rows, and we're also given a target integer. So what we need to do in this problem is we need to, it's kind of in a nutshell before I dive into steps, search the 2D matrix to find our target integer. And then we need to return true if target in matrix, else false. Okay, so as far as our steps, we just need to essentially go through and do a binary search on each row and kind of increase them or decrease them as we see fit. All right, let me talk through this as far as how we want to do it. Okay, so we want to have our left and right pointer, or I guess it's rather than having left and right pointers, we want to make it a little bit more complex as far as how we do this, because we need to have beginning most and end most, and have, I think, the length of both the rows and the columns. And we'll need to have, I guess, the top row and the bottom row. So kind of, maybe we'll have 4 pointers instead. Let me talk through this. Okay, so we need to find, I guess, a variable for length of row and column, and for our top pointer, I think we want that to be, that'll just be, because our top pointer starts at 0 index, you can declare top pointer equal to 0, and our bottom pointer will be equal to the index of our bottommost item. So I think that's just going to be the length of the rows, the last item and the length of the rows. So this will just be and to be row -1. And then we'll need to loop through like a typical for loop. And then in that, we're going to need to see we're going to need to find our middle value from the top and bottom pointer. And then if that is the target, we'll return it. Otherwise, we're going to keep iterating through to find it. Okay. Yes. So we're doing it for the top and bottom point of the what's it called? Of the 2D array / list, and then we'll do it for the rows themselves once we determine a range in which our value will be. Okay. So determine which row has range appropriate for target, binary search that row. Okay, perfect. I want to get started actually coding now. All right, so we're going to find our row. That's just going to be the length. So we have our actual rows. It'll just be the length of the matrix. And then for our columns, we'll have to go into our matrix itself, and we'll just do the column will be the length of matrix at index 0, because that'll get us to our first item in the 2D list, and we'll get column 1, column 2, column 3, column 4, and we'll know we'll have 4 columns. So this will be the length of matrix at index 0. All right, and then we'll have our top pointer is going to be equal to 0, and our bottom pointer will be, we don't even need to do row, or we don't even need to do the length. We'll just be row -1, because we've already calculated that. Okay, so then we'll do while top is less than or equal to bottom, and then we need to see essentially if our middle value is equal. Okay, so we'll do the row. This is kind of finding like the average of the row. So we'll just do our top and bottom value. So these aren't actually the value, but it's finding the indices that's going to be the middle, and therefore the actual middle because of how these are sorted. Okay. All right. And then we're going to go through and say if our target is, I'm going to say greater than our matrix at row, and then we need to find the actual item, because this row is just going to find like which particular row it is. And then we'll do at we'll we'll do it, I guess we'll do the last one. So if our target is greater than that one, we know that we need to have our pointer to be equal to the middle value, which in this case is row itself, or not equal to, but we need to have it be equal to our middle plus 1. All right. I guess left versus right and top and bottom pointer is messing with my head a little bit, but I maybe should have named those a little bit more correctly, or I guess like more accurate to left and right, but we're getting there. And then, okay, otherwise we need to do the opposite. If the target is less than the first item, so we'll do middle value at index 0, in which case we need to bring down our bottom value. And just for clarity, the bottom value or bottom pointer is the greater one and the top one is the large one, because we'll have top pointer, bottom pointer. It is a little confusing, but I think I'm in too deep to rename everything. And then if that's not the case, then we can just break this, because we know that if it's equal, then we just need to find the equal value and return it. But we aren't looking at the actual values just yet. We need to go through and look at the actual, like the entirety of it versus just the rows themselves. We need to look at the entirety of the values. Okay, so we'll just break this, and then we'll do another for loop to actually look at all the values. We have our second pass here. So if our top value is not greater than our bottom value, or greater than or equal to, we just want to return false right here. And this is essentially because we know that if it's greater than, we've kind of passed through the entirety of the values and it will not be equal to one another. So we can just kind of get that out of the way from the get-go. And then now we're going to do a second pass through where we're going to do another while loop with our left and right values for the columns. So the individual values in each row. Now that we've sorted through the rows, we can look at the actual values in the columns now that we've determined which row we need to be in. So we're going to reassign our row to be top and our bottom pointer. And then we're going to divide that by 2 just to get the average of that. And then we're going to set up some normal left and right pointers. This isn't going to be length. I keep forgetting we already have the columns length determined. It will just be column. Yeah. Okay. So now that we've done that, we can do while left is less than or equal to right. So our normal binary search, it'll be similar. We're going to name this actually middle because we're actually looking through a normal list at this point. We're not looking through the 2D list. We've determined which list we need to search for, and we're going to do that by finding the average of these two. And then if middle, I guess we'll have to do if matrix at row at index of middle is equal to target, then we can just return true. Otherwise, we're going to see if matrix at row at middle is greater than our target, then our right value is going to need to be equal to our middle value subtracted by 1. And then otherwise, we're going to need to increase our left value to be more than 1 because we've determined that it is less than our target at that time. All right. And then, yeah, I think after that, we'll just have one more kind of fail-safe return false. And this is just to kind of catch if we find a range in which our target could be. Say, for example, our number was 2. So we determined that the first row is an acceptable range for us to find, for us to look for our target integer. But then we go through this actual list and we find that 2 is not in fact there. We'll still need to return false. All right. I'll return this, or run the test cases, or basic test cases. Our basic test cases are passing. Now let's see if our advanced test cases are passing. Just like yesterday. If you were here yesterday, you've seen my battles with the LeetCode solution. Okay, so all 133 of our test cases are passing. Our runtime beats 100% of solutions, so that's great. Our memory is only beating 2% of solutions. It looks like the values, I guess 60% of the solutions that are beating us are only beating us by 0.1 to 0.2 MBs. So let's see what they did differently. If not matrix or target is none, they returned false. Okay, so this might save some time complexity if you're doing this from the get-go versus letting it run. Okay, and they did something a little different for their top. I guess their low and high was top and bottom for us. We assigned that slightly differently. We just had columns subtracted by 1. So that might have adjusted it. Oh, okay, because they only have a single while loop. So this will be maybe the memory because they have less variables in the while loop. I'm curious to see. So while low is less than or equal to high, they're assigning their middle value and they're finding the number itself. So they're dividing the middle by the number of columns to find which one to access. Oh, that's interesting. Okay. So they're finding, let me pull up the description and then I can kind of walk through this on a sample case and see how it differs. They're multiplying the middle of low and high multiplied by the number of columns. Or they're dividing, okay, they're dividing the number of columns to find the which row they should use. And then here they are also they're using modulus to see like how many remainders to get the individual item for the actual number. Okay, interesting. I'm curious to see how much this in itself will improve the space complexity. I don't think it'll improve much, but I would believe this would increase or better the time complexity. But our solution was beating 100% of runtime. So I guess we have a very similar runtime, but the memory is different because of the single while loop. So let's see if we can do this up here and if this saves us any space. But I'm pretty sure it's just the single while loop versus our 2-pass approach. Okay, this improved our memory by 30%. Okay, so we're kind of like in the midpoint here, and then the single while loop pass brings it up to 12.6, and then we have some, I don't know, math majors who found a hack to get down to 12.4. I always, I guess, poke fun at those like little hacks that sometimes we'll have in DSA. All right. Yeah. Okay. Null matrix, that's what you were talking about. I guess earlier you had made a comment on the null matrix. I guess I didn't catch that, but that's what we found going through this. Yeah. All right. So we've solved our first problem. Great job, y'all. We did a binary search problem. For our next problem, we're going to find the minimum within a sorted array. Or maybe we'll move on to trees. I think we'll move on to trees just to make sure we get in at least 2 problems before the end of our time together. So we're going to start with inverting a binary tree. All right. Okay. I'm going to send this in the chat so y'all are able to follow along as well. I'm going to put this up on the screen, and I'm also going to go refill my water really quickly, and I'll be back in just a second. And of course, drop any questions in the chat, but it should just be like a minute or two. If you need to grab refreshments or go to the bathroom, feel free to use this brief intermission for that as well. All right, and we're back. I have my water. I hope y'all were able to grab some. Okay, but now we're going to move on to our trees. This is a binary tree, and we're going to be inverting it, given the root of it. So if you don't remember from my explanation just a little bit ago, the root is the starting node of a tree. And what we want to do is we want to take the values and invert it or reverse it. So it'll be somewhat similar in like what we're looking for as reversing a linked list like we had yesterday. But it'll be a way different approach. We're going to be using a recursive depth first search approach today. I'm going to break that down up here so y'all are able to see it. Recursive depth first search approach. And I'm also going to talk through this problem itself. As always, make sure to drop any questions in the chat. Looks like we have someone new to binary trees. So feel free to drop any questions in the chat. I want to make sure that y'all understand it. and I'm learning something. And also, if I've made a typo, let me know. Well, let's get started. So we are given what we need to do and what we need to return, if anything. So given the root of a binary tree, invert it and return its root. So we're given root of binary tree. We need to invert the tree, aka all the left children on the right children on the left. And then as far as what we need to return, we need to return root of our inverted binary tree. So as far as how we go about this in a recursive depth first search way, depth first search is an algorithm where you're essentially looking for the farthest you can go down something. Specifically with trees, you're looking to go down to the youngest child, I guess is the best way to put it, about the child that's at like the very bottom right here. So you're looking to find the deepest one. This is pretty easy because like you're inverting it. So it's going to have like the youngest child is going to be the same on both sides. But that's what depth first search is. Breadth first search is where you're essentially looking to see how far across you can go for the entirety of it. And for those of you who are unsure or are unfamiliar with what recursion is when you are calling a function over and over again with just 1 to 2 calls. So you're able to rapidly iterate over something. And that's what recursion is. It's like when you're returning within your function what will be called in the new function call. Yeah, and you can see it in action in just a second here. But yeah, so the first thing that we're going to need to do is create our function. And within our function, what we need to do is essentially just reverse the different roots in our binary tree. So because we're doing recursive depth first search, we're going to want to get down to like the most bottom node within our binary tree. And then we're just going to want to swap them. So it'll be, we're swapping 1 and 3, we're swapping 6 and 9. And then as we go up, we'll swap 7 and 2, and that's it. But in our function, the only thing our function is going to do is swap our left and right value, but only at our current level. So it's only going to be swapping those 2 values when we're inverting it. And then we are also going to want to kind of have a basic like holding value. So within this, we're going to have a holding temp value, so we don't lose the initial value of our left node. And that's essentially it. After we've done that, we'll just need to call it a few times so that the recursion for our depth first search problem can actually start. And then after that, we'll just return our root value of the binary tree. Something nice about LeetCode, particularly for recursion problems and like this particular type of recursion problem, is we're already inside of a function for it to test. So we don't need to create an extra function. We're already creating one when we're writing out our code. It's in invert tree. So we'll just be calling invert tree within itself to get what we need. All right, so we're going to make a basic one, if not root. So if we don't have a root, it's equal to null. That's kind of an edge case here. We're just going to return none because there is no binary tree. There's no root. So we can just return none. That'll get a little bit of, I think that'll save us some time and space complexity because we're not going to be creating more values or doing recursion or attempting to do recursion on a value that does not exist. And then after that, we're going to need to create a temporary value. So this will be temp left And this is just going to be our, not node, root.left. And in a tree, when you have a root value versus having, like yesterday, when we had a linked list and it was data and then our next value, how we access the node itself is going to be left and right. We don't have a next value. How we would access one would just be root.left.left versus root.left.next. I hope that makes sense. And then after we do that, what we want to do is we're going to set our root.right. And we're going to set that equal to our temp value. I did this a little bit out of order. We first want to set our root.left equal to root.right. This is swapping the left value with the right node. And now we have our right value will be set to the initial value of our left root. All right. And then after that, this is the entirety of like us swapping. This is just going to swap one level of the binary tree. Now we need to call it a few times. So we're going to call this on both our left and right values, because as you can see here, there are children of the left and the right. So we need to recursively call it on both sides. So we're just going to call, let's see, it's called invert tree. And we're going to call on it is root.left. And then we'll call invert tree on root.right. So this is going to call it recursively on this until we run out of options, because if there's not a root, we can return none because we've finished that. But we'll continue to call it until we run out of items in our tree. So yeah, that is the basics of our recursion. We have our process here, and this is going to execute recursively on our left binary tree and then our right binary tree. And then after that, we're just going to return our root because we finished our recursive depth first search on both sides. And we have a successfully, hopefully, we'll have to test it first, inverted binary tree. So let's test it. Global name temp is not defined. I left off templates. I got too excited. Global name invert tree is not defined. Oh, I forgot that we need, it's in a class. So we need to call it by self versus just in a normal, with a function that didn't have a class, we could just call it by invert tree or outside of the, like within a larger function. Okay. Silly mistakes, but okay. Now it's passing the basic test cases. Let's see if it passes the big ones. Bane of my existence. Is it popping up on the side? Okay. So it's beating 100% of runtime and it beats 40% of memory. So we're already kind of falling in that default middle. Let's see again what we could have done to make it a little bit more memory efficient. If node.left is none and node.right is none, okay. We will return to end this. Okay. Our temporary value, we're swapping them. Okay, and then this is them recursively calling this. Okay, so I see, I guess they're separating it within within the function itself. So they created a second function, and then they're checking ahead of time if left is none and if right is none before they're recursively calling it. I'm curious to see if this line by itself would improve our memory or our space complexity, because this is essentially just a different way of calling it than what we have, because we're just calling it, we're recursively here versus they're calling it recursively right here. Okay, so let's see if that by itself is going to improve our memory at all. Oh, we need to do root, not node. They altered a little bit of the verbiage. No, okay, so this is having us fail our test cases. I'm assuming because we're ending our recursion maybe a little bit too early, whereas they're calling it if node.left exists and node right perhaps doesn't, then they're recalling it here. Okay. I don't want to just entirely copy what they have. I think that we have pretty good memory on this. It's not most affectionate, or wow, okay. We went from beating 100% to beating 7. So this really shows you how fickle the leak code runtime and space are. I will look at the submissions and see. Okay, so our runtime went from 0 ms to 1, and our memory went from 12.6 to 12.4. And I changed literally nothing. Let's submit it again and see what it is. No. Okay, so we're getting the same as what we had before, but our memory is more efficient this time. Okay, so it really shows to like not take to heart too much the amount you're beating on lead code, but more to look at the actual like milliseconds or millibytes of your memory. So yeah, I think we did pretty good. Thanks for joining, or yeah, thanks for tuning in for our tree segment. So we're going to dive into another tree problem. All right, let me see if there's any questions I missed while I was beat coding. Or I hope you were able to understand the binary tree problem, or were you confused about it? If you have any like questions or didn't understand something I did, feel free to drop that in the chat. I want to make sure everything's clear and you're understanding it. Yeah. Yeah. Okay. There's a question. It's late wherever you are. Is today the last day? It is the last day of Global Hack Week. But if you are tired and you'd like to go to sleep, feel free to. All of the recordings or all the sessions from Global Hack Week will end up on Twitch and YouTube for you to view later. Sometimes it takes a little while for them to get uploaded, but the one from yesterday I did is already up on YouTube under the live section of Major League Hacking. So you can go to sleep if you'd like to, but today is the last day. All right, so we've done our first tree problem. Let's move on to a new one. Maximum depth of binary tree. So in this one, let's refresh it so my prep work isn't visible. In this one, like the title is saying, we need to return its maximum depth. So we're just trying to find how many levels are in this binary tree, and then we need to return it. And like it says here, a binary tree's maximum depth is the number of nodes along the longest path from the root node down to the furthest leaf node. So yeah, we'll have the longest path down is going to be 1, 2, I guess no. From the root node down to the furthest leaf node. I'm just slightly confused why this one is 3 instead of 2. but I guess it is counting each node instead of the connections, it's counting the nodes. Okay, that makes sense. Yeah. Okay, cool. So let's do given, do, return. So we are given the root of a binary tree. We need to find, oh, if I had read this more closely, I would have known that from the get-go. It says the number of nodes, like straight away, instead of the number of, I guess, jumps. Find max depth in binary tree. And we need to return the integer of max depth. All right. And okay, looks like no questions. So we're gonna keep going on our merry way. So the first thing we want to do in order to find our max depth is we need to essentially run another recursive depth first search program on this, but it's a little bit less complicated because we just essentially want to count how many nodes we're finding on our journey for depth first search throughout this program. So we don't even need to do as much as we did last time. Last time we had our swapping. This essentially we just need to count as we go through in our recursion. So in that, I think what we're just going to do is reassign. I think we'll just be like increasing the count by 1 every single time. But first, so we'll do recursion. I'll put this up here. Recursive depth first search. And then this will be more simple. So what we'll need to do is increase, I guess, as recursion occurs, and we operate a depth. Let's shorten this algorithm. We need to increase count of max depth by 1 for each node. Yeah, and then we'll just return the final value at the end that we find by adding together or by returning the maximum. Okay, so similarly to last time, we need to check if there's not a root because we don't want to go through like attempting recursion or our depth first search algorithm if there's not actually a node, if there's not a root. So if that happens, we're just going to return 0 because there are no roots or nodes for us to go through and do depth first search on. So we can avoid all that headache and time complexity by just returning 0. And then after that, we're going to count our left depth and our right depth. And we're going to do this recursively. And this is where it might get a little bit confusing, especially if you're new to recursion or depth first search. We don't even need to have anything as a base condition before we start running recursion. So we're just going to have something pretty simple for recursion, at least. We're going to have self.maxDepth, and stick with me, y'all. I know it's going to get a bit confusing. And then we're going to have root.left, and then we'll have root.right, because this is going to be the right depth, or this is going to be the right depth and the left depth. So we're recursively calling it before we're actually doing anything. But after that, what we're going to do is we're going to return the maximum value of either of those, because as we go through this will increase with our return statement we're going to put down here by 1 what the value is. So we'll have returning the maximum of our left depth and our right depth to find our maximum node depth. And we're going to increase that by 1, just because once we get to the end, it won't be not once we get to the end, because it's not counting the root node itself. It's just beginning our recursion on our left node and our right node. So that's going to iterate over it, count those nodes as each one continues, and then we'll add 1 to account for the root node itself. Let's try our basic cases. Those are passing, and we're going to submit. All right, our solution, it looks like it was accepted. LeetCode is not my friend lately. I need to figure out how to permanently fix this because it's bothering me. All right, and then we have our runtime is beating 37%, and our memory is beating 14%. All right, I'm curious for runtime what 25% of people were doing for 0 milliseconds. Okay, so, oh, they're doing everything sneaky. Okay. So to save on runtime, instead of having the depth first search recursion declared as variables, they're just putting it straight into the return statement, which I had not thought about. That's really interesting. I'm curious if we move that, if that's going to affect our memory as well, because we won't have those 2 variables. I guess the code is a little bit less clean to read because basically the entirety of the operation is on 1 line, or I guess 3 lines. You count this as well. I would have never thought of that. This is what I mean by, I guess not really. This is just a hack being a little bit clever about it. All right, so the runtime is beating 100% because we're at 0 milliseconds. It looks like the memory is about the same though. Yeah, the memory is the same. Okay, I'm curious for memory. We're beating 14%. What the people, looks like 8% used 14.9, which is a good amount less, but not crazy less. They have a lot of code for this. So they're returning this, but within their max depth, they're setting their left equal to node info, max depth is equal to left. Okay. So instead of storing everything inside of the, function, I guess hard coding it out, make like into a specific node info makes the memory slightly better. Interesting. I don't think I would go with that approach just because it's not saving a terrible amount of memory. And because there's, I guess 39 test cases isn't a terrible amount of test cases, but it's testing it with larger data sets and it doesn't seem to be saving all that much memory. But I would implement this clever little hack just because it has, and saving us a significant amount of runtime. Going from 4 to 0 is a little bit more significant than 15 to 14.9. All right, so that is our second tree problem. Congrats, y'all. I know we're kind of cruising through these just because the solution is a little bit more simple than other problems than our binary search problems. But we do have one more tree that I want to get through before the end of our time together. So let's go on to the diameter of a binary tree. Let me refresh my prep work. And then we can go through the explanation of what this is looking for. So we're given what we're going to do and what we need to return. So given the root of a binary tree, we need to return the length of the diameter of the tree. So instead of finding the number of nodes that it takes to get to the bottom of a binary tree, we need to essentially see what is the widest part of this tree. And we're going to do this. This is what we call breadth first search versus depth first search. Yeah. And for this one, I think I want to talk through the specifics of this a little bit more. So we have, given the root of a binary tree, and we need to return length of diameter of the tree. Or no, is it talking about this again? Interesting. So instead of calling it, I guess because of like how, interesting. Okay. So scratch a little bit of what I said before. I got a little bit over eager. We're not looking for a cross. We're still looking for the longest path. And then we're also looking for the length of the path. Okay. So let's look at this explanation a little bit. So we have our binary tree here. And the output is 3 because the length of the path 4, 2, 1, 3, okay, has 3 connections. Okay. So we're looking for, I guess I was kind of right. So instead of just looking from like the root to the end for our count, what we're looking for is edge to edge. So we do want to cover across, but we're not just going straight across. We're going through the edges. And this length will be represented by the edges that are connecting them versus the actual nodes that we're counting. Okay, so we need to, this will still be, I think this will be breadth first search instead of depth first search. Yes, this will be a depth or breadth first search. Okay. So as far as what we need to do is we need to go through and count however many edges we have. Count the edges we have while going on journey from left to right node. Okay. And similar to previously, if we don't have a root, what we need to do is just return 0, because if there's no root, we have no problem. And we can't go through and do everything. But I don't think we need to return, is it 0 or -1? I guess if there's not a root, we would need to return -1, because if we have a single root, it would, I guess there's no edges. It doesn't say. So I want to try, I want to try 0 and see what happens. And then if it's not working, then we can continue on. And if we do have a root, then we need to start counting our edges. So we're going to go through and recursively find the length of our left and our right edges. But in addition to that, we need to find, we need to find the maximum for the counts, because we need to essentially piece them all together. And I think that the best way to do that is going to be through, I think it's going to be through holding it in a list, and then we kind of combine everything together. Okay, so I'm going to make a list to hold some information, and then we can process our recursion a little bit easier. So we'll have the result of how many edges we have, and we'll set our default value equal to 0. And then after we have done that, or we have our default value has been set equal to 0, we're checking, we make sure that we actually have a root value, and we're going through and we're recursively finding our value. Then we need to go into our result and set that equal to the maximum of our, I think, our current value, and then everything added up together. Okay. Set that equal to the maximum of result 0. And then the second one will be left plus right. We want to do both of them together because we're essentially finding the maximum depth on both sides and piecing them together, because we want to get from the lowest point on the left to the lowest point on the right. We're going to need to add up all the edges together. And then I think we're going to add 2 to the maximum value, or to this maximum value right here. Just because I think that how we're recursively calculating this is not going to get our edges up to the proper count versus how we're doing it with the nodes. Because if there's not I guess it's because, sorry, scratch that. The reason we need to add 2 specifically is because we're going to have these children at the edges at the lowest points that we need to account for. So last time we weren't accounting for the node in our problem, which is why we need to add an extra one. Now we need to add 2 because there's the bottommost node on both the left side and the right side. Okay, so we're calculating the maximum and then joining those together. And then we need to actually return our value. So we're going to return our result at 0. And then we're going to, no, we're not going to return our result value just yet. Let me talk through this again. Okay, so we have we're making sure we don't have a root value. We're recursively calculating how many edges there are on the left and right side. And then we're setting our result to be a value that has the maximum of what it's currently holding, and then the number of edges. But as we're calculating this, we don't need to return result quite yet. I think we need to do that we need to find the maximum of our left and our right and return that. So as it's recursively calculating this, we'll be able to add that value up a little bit easier, because there's multiple things we need to have in consideration for this recursion versus just the left and right, like the last problem. So we'll return 1 plus which one is larger of left and right. Also, this particular recursion case, I think we need to house in a more separated function, just because of how this particular problem is. So in here, we're going to house the count of our diameter. So we'll just have count diameter. And we're going to put in our root, because we need to feed in the root value that we're getting up here. And then out here, we need to actually call it. So we'll have our count diameter, and we'll call the root value on it initially. And then after that, we can actually return the result itself because we've calculated it up here. And once it's recursively run on both the left and the right sides, we can return our result, which will be that calculated edge case. Okay, that's making sense to me. I'm going to run that, see if it's making sense to the computer. And if y'all have questions, oh no, count diameter. Oh, this needs to be self.count diameter. Huh. Okay. I misspelled diameter. Okay. Name result is not defined. I think that I need to put this as a global variable. No. Okay. So we're getting 10. We're expecting 3. I guess let's see what's going on here. Okay, so we have our result variable. Maybe it's coming from this, where earlier, if this is set to 0, the edge case maybe needs to be -1. This might allow for that element of recurred. Oh, my power strip to fall down. There we go. This instance of recursion, it will subtract 1, sort of adding 1 when we've maybe gone a little bit too far because we're not checking to see if there's a left and right of our root. Let's see if that is correct. Nope. Okay, so we're still getting the same thing. It's not that. Okay, so we're checking that there's not a root. And if not, we are recursively, oh, I see. Okay, so we're not actually recursively calling this right here because since I added in another function, this is calling the entire function again. That's only doing this, calling the damp number again, which is causing the count to be much higher than the actual edge cases. So this needs to be count diameter instead of diameter of binary tree. I should have, I guess, realized that I needed the second helper function ahead of time. Attribute has no solution. Attribute has no count diameter. Do I maybe need to get rid of self because it's not the larger function that's inside of count? It's a nested function. Okay, that was accepted. So that's passing the preliminary cases. Fingers crossed. I adjusted all the function calls that it's passing all the cases now. Okay, yes. So it's beating 56.92% of other solutions for runtime, and our memory is beating about half of them. Where you get the applause symbol for both of them, I'm a little curious on LeetCode why you get the applause versus not for time and space complexity. I feel like it really depends on the problem. I'm curious for runtime solutions that use 7 milliseconds. So similar to us, they had this, we had this, the height which is what we're determining as well, height, diameter. Tomatoes in this case. They're taking the best of, okay. They're not adding on 2 for the missing nodes. But they're, okay, they're returning the maximum and the diameter. Huh. It's curious that not adding in the extra 2 nodes is still working. I'm curious if we delete that. That's the only actual difference. And I'm curious how we're getting the same numbers too. Yes, it is actually maybe calculating those. Oh, I think no. Okay. I think these are the same now. Let's see how it varies. If it still passes. If I read that correctly. Nope. Okay. So it is missing those 2 nodes. Let's see what is different and how we're calculating this. Maybe they're just calculating it on the root itself. So we have if not node. Moving the left and the right. Oh, they're returning 0 instead of -1. So they're not changing that value whatsoever when we get down to the last value. But it's saving them time complexity, I guess, because they're not subtracting every single time. They're just leaving it the same. Huh. Interesting. Okay, so our memory is now really good, but our runtime hasn't really improved. Our runtime got worse, actually. Okay. But I found it on, I don't know if yeah, it was on 7 milliseconds earlier. Wonder if there's anything else different. You have, yeah. It looks, I guess there's no else statement. That shouldn't be affecting, it should functionally be the same. Huh. Now I'm curious. You can spend a lot of time tinkering with stuff on LeetCode like this if you look at other solutions and that are more optimal and kind of seeing what actually made it more optimal. Okay, now the runtime is, it's beating 40%, but I don't think it actually changed all that much. Okay, it went back, it's in the middle now of our initial submission. Okay, I think I'm just going to uncomment all this, or unchange, return to our initial submission, because it looks like we had better runtime when we started. I'm just gonna, now we have 7 milliseconds of runtime. So I think that LeetCode is literally comparing you to who's submitting in that moment, because now we're down to 7 seconds of runtime instead of 14 or 12 like when we had initially submitted. So I'm just gonna call it a day. Looks like our memory is a little bit worse, but we're not gonna get into it. What I do want to get into briefly is the time and space complexity of these, just because we talked about that earlier. I meant to be a little bit better about this in the moment, so that y'all can kind of see it applied in real time. But for our time and space complexity, I typically just add it as a note here. So we have our time and space. So our space, I believe our space is just going to be constant because we're just declaring kind of basic variables. So we'll just have that be O1. And as far as our time complexity, because it's recursive and we'll continue to call our function as many times as there is a left root and a right root, that's going to be a linear time complexity. So O of n. Yeah, so that's the time and space for this one. Nice job on finishing the last tree problem with me. I think now, so let's do a quick time check. We have about 10 minutes left together. I'm going to do the time and space complexity on the other 2 tree problems we did. and then we can dive into any questions and provide some more resources. Yeah, okay. So for which one around? Diameter, so let's go to the maximum depth. So here, I think for our time complexity, it's definitely just going to be constant because it's a recursion problem. It's just going to be not constant. Our time complexity will be linear, not constant, because we're just going to continue calling it while we have left nodes and right nodes to continue to call this on. As far as our space complexity, I think it'll just be constant. We're not necessarily creating any new like values, but it's constant is like the lowest, I believe, space complexity you can have. And then for inverting a binary tree, we can go in here and let's see, for our time complexity, that's going to also be linear because it also has recursion. So we'll have what we have here, time, space. And then for our space complexity, these are all just kind of temporary values as we swap them. So it's going to also be constant, I believe. All right, that was a little bit boring, but I hope that me talking that through for those problems is a little bit helpful in you understanding the problems a bit better and how to calculate the time and space complexity of things. Yeah, all right. So now I'm going to go back to my slides. We can go to our last slide where I have some links. So there are a few short links on here. DSA 101 slides is where you'll find the slides here that have the master links to everything and where you can find the material that I went over in the session earlier and in our first session yesterday. If you want to go back and see that, read it over a little bit more, I'll make my adjustments to typos. If you go to DSA 102 code, that's where I will upload all the code onto GitHub into a repository that we went through today. So that will have the solutions as well as the notes that you saw on my screen. And I also want to call out mlh.link/GHW feedback. This is the Major League hacking feedback link where you can submit your feedback on this stream, what you enjoyed about the stream, learned anything new, how your learning process went. If there was anything that I can improve or Major League Hacking can improve, you can put that in the feedback form as well. We're always looking to make Global Hack Week a better experience for y'all. And then I do want to call out two resources up at the top here. We have NeetCode and we have CodePath. NeetCode is a wonderful resource if you're getting into data structures and algorithms learning. They have this pretty simple roadmap of how to prepare for technical interviews. If you were with us in January for the 101 session, most of the material we covered were arrays and hashing. And as you can see, those are kind of the basics of data structures and algorithms. I have personally completed all of those problems, and I'm starting to work my way back through the rest of this tree. We went through 2 pointers last session, as well as, I guess, kind of technically a little bit this session. 2 pointers of building blocks for binary search. I'm getting a little bit too in depth here, but essentially this is a roadmap for data structures and algorithms. It'll have links to LeetCode problems as well as video walkthroughs and solutions for the problems. So we went through my solution and thought process for a few problems today. The guy behind NeetCode has done this for like hundreds of problems. If you just search whatever LeetCode problem you're stuck on, followed by NeetCode, you'll often find a solution walkthrough, and I find the visual and verbal element of it to be very helpful for my learning. So if you ever get stuck, this is a super helpful resource. Also just like a good way to find like what problems to focus on for getting a good understanding of like a wide variety that will be helpful to your understanding of data structures and algorithms. My second resource I wanted to share with y'all is CodePath. So CodePath is unfortunately just for college students and recent graduates, I believe, but they have a lot of courses on data structures and algorithms. I personally went through their technical interviewing 101 and 102 courses. They're beginner and intermediate courses for data structures and algorithms. They're super, super helpful if you are looking for an internship or a full-time job. This is like dedicated time to practice these problems with your peers, and they'll give you feedback. You'll talk through them together. So you go from being super confused to understanding them, and you'll also have lecture time. These are all completely free classes. They have other stuff as well, but I wanted to highlight them because their data structures and algorithms courses are incredible. I went through them myself. Like I talked about, technical interview prep is what I went through. They have a bunch of other stuff, but yeah, just wanted to shout them out. I think it's a very good resource for this type of stuff. But unfortunately, just for my students in college, if you're not a college student, I apologize. But I really love their stuff. Yeah, so that is all I have for y'all today. We're getting close to 9 Eastern. I'm going to pull back up the registration link for this particular session. It'll be events.mlh.io/events/13709, and that's where you register your attendance. This makes you eligible for any giveaways that Major League Hacking might have going on, or also just bringing you closer to different achievements, and also gathering a little bit of intel on our side as far as what y'all are interested in and what you enjoy. As far as question 2, I'm not going to bring it up on screen because I want to keep the registration link active. Dumpsters Alley asking about the goodies. There isn't a goodie drop or swag drop for this particular stream. Sometimes on Today in Global Hack Week streams or in the Discord, there will be different giveaways. Sometimes they're related to challenges. Sometimes it's your participation points. So that's why I pointed that out. There's not any particular swag giveaway on this stream, unfortunately. My apologies if that wasn't clear when I started. But yeah, are there any other questions? How did y'all find the content? Did you learn something, I hope? Yeah. And how's your Global Hack Week been going so far? I have personally enjoyed these streams, this 2-series streams with y'all. And I always learn something myself as I'm going through and problem solving with y'all live. So thanks for tuning in. All right, I'll give it like a minute or so to see if there's any more questions. All right, I don't think there are any questions. So in that case, thank you for tuning in. Be sure to check out the remainder of this Global Hack Week, and future Global Hack Weeks will have information on our site. But I'll see y'all in the Discord. That's where I'm going to drop the short link to these slides in just a few. But thanks for tuning in. Happy hacking. See y'all later.